So now we're going to learn about ellipses, and we've already dealt with circles a good bit, and really a circle is just a very special form of an ellipse. So our formal definition tells us the ellipse is formed by taking the set of all points in a plane, the sum of whose distance from two fixed points is constant. Each of those fixed points are going to be called a focus, and plural you can pronounce them as foci. So we're going to start by figuring out all the important properties about an ellipse with center at the origin, just like we did with a circle centered at the origin. And then afterwards, we're going to go ahead and move that off that origin. So we'll move it to some center HK. And all it's going to do is really shift all of the important pieces. So we have two cases we're going to consider, and they both look very similar. So your form for an ellipse is going to be x squared over a number squared plus y squared over a number squared equals 1. And then same thing over here. One of those numbers is going to be bigger than the other in the bottom, and that's going to tell you where the important pieces of information are going to lie. So in this first case, the number under x is larger, so all the important stuff is going to be in the x direction. Here, the number under y is larger, so all of the important stuff will be in the y direction. The numbers that are underneath each of the variable are just going to tell you how far off the center you're going to move. So basically, we have two axes for our ellipse. One's the major, one's the minor. The major axis is where that important information is going to be. So here in our first case, I've got that center right at the origin. So it's going to be right here. The numbers underneath each variable tell me how far out I move from the center. So x has an a squared underneath it. We're going to move out a distance of a. So this will be the point a0. Then you go the other direction, a distance of a. This will be negative a0. The value that's underneath y tells you how much you move in the y direction. So we've got b squared underneath y. That tells you you move up a distance of b and down a distance of b. Okay? And then those dots will be connected to form our ellipse. Okay? So the major axis is going to be connecting the two vertices. So the length of that is going to be 2a. The minor axis is connecting the less significant points, and the length of that is going to be 2b. Same thing in this case. Your length is 2a and 2b. So in the case that y is larger, you still have your center value here. You're going to go up and down the same distance. So this vertex will be 0a, this vertex will be 0, negative a. And I don't go as far out in the x direction because that's my smaller one. And you go out a distance of b in each direction. And that is going to be our ellipse. Okay, so the foci are going to lie along that major axis. So here, our foci will be along the x-axis, and here they'll be along the y-axis. So the way this definition is formed is if you take a point on the ellipse and you look at the sum of the distances from each foci, it'll be the same regardless of the point you pick. So if you pick the point here and look at the distance, some of those distances, it's exactly the same as that first one. So you're always going to get that same fixed value. So these 2 points are called our foci. And all you do is move off the center a distance of c. So this one would be negative c0. This will be c0. Likewise, this will be 0c. This one will be 0, negative c. And those are our two foci. To actually find the value of c, we kind of have what's like a reverse Pythagorean theorem. So in both cases, to find what that number c is, you use c squared equals a squared minus b squared. So it's just going to come from this triangle that ends up getting formed between these two. Okay? So let's go ahead, let's try to come up with the equation of ellipse. We want to find the standard form of the equation of the ellipse with foci at plus or minus 2, 0, and we're told the length of the major axis is 6. So if you're given a bunch of information, I'd recommend always graphing it first, because that's going to tell you which direction this ellipse will open up in, where your vertices should lie, which are the endpoints of the major axis. And then it'll also help you figure out all the information that's going on. So right now I know what my foci are, which are -2 and 2. So here are the foci. Okay. My center is going to have to be halfway between these two, which happens to be at 0, 0. So we're okay. It's going to have the same form as above. Now, we're also told the major axis has a length of 6, and because those foci are stretched out on the x-axis, that's where the major axis is going to have to lie. So the way you can think of that is the length is 2a, so half of that is your value of a. So if I want to find the endpoints or the vertices of my ellipse, starting from the center, you go out a distance of 3. So here's one vertex, and I go back a distance of 3. So the length between these two is exactly 6. So now I can use all of this information to really kind of help us get that equation. And so your vertices will be at plus or minus 3 and 0. So I'm going to pick all my information. A is equal to 3. C is going to be that distance out to the foci. So that's this distance here, which is 2. And then I need to figure out what B is to figure out what goes underneath Y. And so we're going to use those to find B. Since C squared is A squared minus B squared, you plug in those values, subtract the 9, or add it over. You're going to get that B squared equals 5. So B equals the square root of 5. You don't need the plus or minus because this value of B is representing a length. So you only care about that positive part. So now I can actually write the equation of our ellipse. We know it's x squared over a squared plus y squared over b squared equals 1. What goes underneath x is 3 squared, and then under y is root 5 squared. So this is the equation of our ellipse. Okay. So if you're given information about it but not the equation and have to come up with it, definitely draw everything so you know what's going on. So now let's try the opposite. Let's work with the given equation of ellipse, and we want to find all of the important pieces of information. So we want to find the vertices, we want to find the foci, domain, range, and then we want to graph it. So when I start with this equation, remember those values underneath the x and y are squared. So the square root tells us how much we have to go out in. So I'm just going to rewrite it. So I've got x squared on its own. That's the same as x squared over 1 squared. Y squared over 16 is y squared over 4 squared. So immediately can also pick off that that center is 0, 0. To figure out where the important information lies, I've got to see which one of these has the bigger denominator. So the y squared has the larger number, and you can see that here too. The major axis is going to be along the y-axis, and the length will be 2 times the square root of the number. So it'll be 2a, which is going to be 8. So I've got my pieces of information. My a is equal to 4. The value that I'm going to go off in the x direction is 1. And then I need to go ahead and figure out what c is to be able to find my foci. So we use c squared equals a squared minus b squared. So that's 16 minus 1, or 15. So that's going to give me c is equal to root 15. So before I actually find all of the vertices and everything else, I'm going to plot it all. So I'm going to start by plotting our center, which is at 0, 0. Now my y has a 4 underneath it, so I'm going to go up and down a distance of 4. And then my x has a 1 underneath it, so I go left and right a distance of 4. And then I'm going to connect those dots to form my ellipse. My value of C is root 15, so if I want to find those foci from the center, I'd go up and down a distance of root 15, which is a little less than 4. So it's around here. So this will be a distance of root 15, and same thing, you go down a distance of root 15. So you can utilize this to actually come up with those vertices and foci yourself instead of trying to memorize formulas. But the vertices occur at those large endpoints of the major axis. So in this case, that's 0, 4 and 0, negative 4. The foci will occur at 0 plus or minus C, or from the center you go up and down a distance of C. So that's at 0 plus or minus root 15. For your domain, my x is just going to be the x values that are going to be on that minor axis. So my x values are trapped between negative 1 and 1 because I can only go out a distance of 1. And then my range is going to be what the y values can vary between, and I can't go past 4 and negative 4. But I can equal each of the endpoints in these cases. Okay. So now we're going to go ahead and we're going to shift that center. And so I want to move it to HK. All that's going to do is shift every single component. Doesn't change how you find your value of C. Doesn't change how you go about the process. You always plot that center. You go up and down what's underneath Y. Left and right what's underneath X. Your equation to find the value of C is still the same. To actually find the foci, you go up and down that distance of C, or left and right, depending on where the major axis is. So instead of trying to write all of those formulas and make it a little bit gross, I'm just going to consider the case where you have a squared as the larger quantity, so everything is going to open in the x direction. So what I want to do is I want to first plot that center. So we've got HK right here in the center. Here's H, here's K. So what I want to do to figure out my endpoints or my vertices is I'm going to kind of ghost in a new center coordinate system. So here's if the y value stays the same, and here's if the x value stays the same. Okay. From the center, to get to those endpoints along the major axis, which is in the x direction still, you're going to go left and right a distance of a, wherever that ends up. So in the x coordinate, you're going to add a, but the y coordinate stays the same. To get this other endpoint, you subtract a, but again, the y coordinate stays the same. So these give you your two vertices. Okay. Now if you want to see the other endpoints in the y direction, from the center, you go up and down a distance of b. So I keep the x coordinate the same, but I have to add b in the y. I keep the x coordinate the same, but I subtract that value of b in the y. And then your ellipse connects those dots. So this is the distance a from here to here. This is the distance a from here to here. And then same thing, this distance is b, this distance is b. To find your foci, you're going to move left and right that distance of c, because everything important is going to be in the x direction since that has the larger quantity. So I add this distance of c and subtract the distance c. So if you want the equation of the foci, that's just affecting the x coordinate. Again, the y coordinate is going to stay the same. So the best thing you can do again is plot these, take it step by step. You don't need to memorize formulas for all of the endpoints. So let's go ahead and graph one of these types of equations and do the same thing. We're going to state the vertices, foci, domain, and range. So if I look at these two, the bigger quantity is underneath the y value, so everything important is going to be in the y direction. But first, I'm going to go ahead and rewrite it just to know how much I move up and down and left and right. So underneath the x quantities, I've got 3 squared, 4 squareds underneath the y's, and that equals -1. So this tells me my center is going to be at 2, -1. So the first thing I'm going to do is plot that. Here's our center at 2, -1, and then I'm going to go ahead and ghost in some straight lines to help us out with all of our endpoints, vertices, and foci. Okay. So I know this is going to open in the y direction. My value of a is 4, my value of b is 3. And if you want your value of c, it's going to be a squared minus b squared. So 16 minus 9 is 7. Our value of c is the square root of 7. So to find my vertices, starting at that center, I'm going to go up and down a distance of 4. So this would be 1, 2, 3, 4. And that's going to land me right here. So this first vertice is going to be at 2, because I didn't change the x, but I added 4 in the y coordinate to get to 3. So you can even put in that this is 2, -1 here to help you out. To get my other vertex, I go down a distance of 4. So that's 1, 2, 3, 4. And it would land me right here at -5. So this is 2, -5. So our vertices are really, you add that distance of a and subtract the difference of a in the y coordinate. So we get 2 points, 2, 3, 2, -5. And again, you don't need the equation. You can just do that straight from the graph itself. Now for the other endpoints, for the x, I have to move left and right a distance of 3 because that's what's underneath my x. So I go 1, 2, 3, and we land right here for our other endpoint, which is going to be at 5, -1. Then we go ahead and move left, 1, 2, 3, and we land right here at -1, -1. So those are the other endpoints. And then we connect the dots to get our ellipse, which looks a little circular, but it's okay. Now for our foci, from the center, I have to go up and down a distance of c, which is root 7. It's a little bit less than 3, a little bit more than 2. So I have to go up a distance of root 7, which is 1, 2, and a little bit. So here's 1 foci. Then I have to go 1, 2, and a little bit. And that's down a distance of c. So the equation for our foci are going to be, I just move that distance of root 7 in my y coordinate. Then for our domain and our range, I just need to figure out what are the endpoints of the major and minor axes. For our x values, we're trapped between -1 and +5. For the y values, we're trapped between -5 and 3. Okay. Now the second type of problem you can run into, and we're going to see this in the next section's homework as well, is you can have an equation of ellipse, but it's a little bit hidden. So we're going to work with this equation, and we want to graph it and state the domain and range. So if you look at this, the first thing you kind of have to recognize is you've got a square root here. And one thing that's special about square roots is they're always greater than or equal to 0. So really, our y value being that square root gives us that this y over 2 has to be greater than or equal to 0, or really, I only care about y being non-negative. So I'm not going to get a full ellipse from this. I'm only going to get a portion of it instead. To actually see that this is the equation of ellipse, we're going to work with this, and we're going to go ahead and square both sides. So if you take y over 2 squared, you get y squared over 4. On the right-hand side, the square and square root cancel. Now, if you go ahead and add this piece to the left-hand side, we're going to see this is an equation of ellipse. And the center of that ellipse is going to be at 0, 0. So it's really an ellipse, but since I only care about y being non-negative, we only get the top half of it instead. So that center is at 0, 0. The x tells me you move left and right a distance of 5. And what's underneath y would tell you to move up and down a distance of 2, but I only care about moving up 2. So a equals 5, b equals 2, but I'm only getting the top half of this ellipse because that square root was in there. So my domain wasn't affected. I can still take on all the x values from -5 to 5, but my range is only going to be from 0 to 2. So just be careful when you have these hidden forms with that square root, you're going to restrict it to just a piece of the conic section. Okay? So this whole unit is really about conic sections, and all that really is it comes from the fact that these shapes are formed from the intersection of a cone. So if you think of a waffle cone kind of put back to back on top of each other, if you slice through that cone at an angle, you're going to see that it could be an ellipse or a parabola, or in the next section you'll see we have hyperbolas too. But they're all formed so that there's some ratio with distance and fixed points being constant. For us, it's if I take any point here and I take the sum of the distance from the foci, that's a fixed constant, regardless of the point I pick. In other types of conic sections, it'll be a different ratio or different formula to figure out what that fixed distance is going to be. But the constant ratio that happens is called the eccentricity. And so you could look up more information about this if you want. It's going to be denoted by a boldface E. Your book will go through kind of how this value of E is found, but it's a little complicated and it's not worth the time to go through. So instead, I'm just going to give you the definition of what it is. For an ellipse, the eccentricity is kind of telling you how round it is. So if it's got a small eccentricity, it's going to be closer to a circle. If it has a large eccentricity, it's going to be a very squished ellipse. So anytime we have an ellipse, because we have that formula c squared equals a squared minus b squared, we always are going to find that the value of c is smaller than the value of a, because your foci have to lie in here. This distance is c, this distance is a. So we get this relationship. So if you divide by a, you're going to get this ratio c over a is less than 1. And that's exactly that fixed ratio for this conic section. So this is going to be our eccentricity, which is denoted by a boldface E. So every ellipse has eccentricity, which is defined as c over a, and it's going to be some constant between 0 and 1. So it's just going to be a simple formula that we have to plug in to find the eccentricity. So let's look at this ellipse. X squared plus x squared over 8 plus y squared over 4 equals 1. Let's find the eccentricity of it. Your value of a is going to be what's underneath the x because it's the larger quantity, so it's the square root of 8. I need to find my value of c, so to do that, I need to figure out what b is. So then c squared is a squared minus b squared, which is 4. So now I get that c is equal to 2. So our eccentricity E is going to be c over a, which is 2 over root 8. And if you go through actually rationalizing this, you'll see it's root 2 over 2. But if you plug it into your calculator, it's about 0.71. So again, a number between 0 and 1. So that would tell you this ellipse is kind of oblong and it's not circular in shape. It's not very round. It's more flat. So let's do one more. Let's look at x squared plus 25y squared equals 1. So this isn't really in standard form yet, so I've got to rewrite it. To bring that 25 in the denominator, you write it as 1 over 25. So that's x squared over 1 squared plus y squared over 1/5 squared. So the larger quantity is actually underneath x. So a is equal to 1, b is equal to 1/5. So c squared is 1 minus 1 over 25, or 24 over 5. So your value of c is going to be this, which if you rationalize is 2 root 6 over 5. So your eccentricity is c over a. So it's 2 root 6 over 5 over 1, which is just itself, and that's about 0.98. So you would see this is a very flat ellipse. Okay. So you're going to see a similar formula when we deal with the hyperbola. It's really going to be exactly the same. It's just going to be a quantity that is bigger than 1 instead. But there's some really nice applications of this when you talk about eccentricity or define a conic section in terms of its eccentricity. So if you've ever heard of Kepler's laws or planetary laws, those deal with the eccentricity of ellipses. So it's a pretty cool thing you can look into, but we're not going to spend a ton of time focusing on it.